Asteroids, the rocky remnants of the early formation of our solar system, have always fascinated scientists and alarmed them because of their potential threat to Earth. Of these, the asteroid Bennu has received considerable attention due to its size, proximity, and potential risk of collision. Discovered in 1999, Bennu is a carbonaceous asteroid that poses a serious threat to our planet, prompting scientific efforts to understand and possibly mitigate this threat. This article discusses the characteristics of Bennu, scientific efforts to study it, and notes the views of astrophysicist Neil deGrasse Tyson on the possible consequences of an asteroid impact. Bennu is a near-Earth object, NEO, discovered on September 11, 1999 by the Lincoln Survey of Near-Earth Asteroids, Linear, project. It is a carbonaceous asteroid classified as B-type due to its composition, containing significant amounts of carbon and primitive materials. With a diameter of about 500 meters, Bennu's orbit brings it relatively close to Earth and crosses the path of our planet every 6 years. This proximity, combined with its size, has made Bennu one of the most dangerous asteroids known, with the potential to have a significant impact. Bennu's orbit around the Sun takes about 1.2 years, making it an Apollo-type asteroid that crosses Earth's orbit. Its trajectory is affected by the Joukowsky effect, a force caused by the absorption and re-emission of solar radiation that can change the path of an asteroid over time. Bennu's surface is covered with rocks and loose material, suggesting that it is a rock-pile asteroid, a collection of rocks held together by gravity rather than a solid body. If Bennu were to hit the ground, the impact would release a massive amount of energy equivalent to millions of tons of TNT. Consequences depend on the location of the impact, with potential consequences ranging from massive tsunamis if it hits the ocean to widespread land destruction and atmospheric disruption if it hits a populated area. Scientists use complex simulations to predict these scenarios, helping to influence mitigation strategies. The potential threat posed by Bennu has spurred extensive scientific research, particularly through NASA's OSIRIS-REx mission. Launched in 2016, the OSIRIS-REx spacecraft was tasked with traveling to Bennu, mapping its surface and collecting samples to bring back to Earth. The mission provided valuable information revealing Bennu's surface composition, rotational dynamics, and internal structure. This knowledge was crucial for estimating the probability of an asteroid collision. Current estimates put the probability of Bennu hitting Earth at the end of the 20th century, around 2,182, as 1 in 2,700. Although these probabilities are relatively low, the potential devastation of a collision requires continued monitoring and investigation. The OSIRIS-REx, origins, spectral interpretation, resource identification, security, Regolith Explorer mission is a major step forward in our ability to study asteroids up close. After a 2-year journey, the spacecraft arrived at Bennu in December 2018. It spent several months mapping the asteroid's surface with high precision and identifying suitable locations for sampling. In October 2020, OSIRIS-REx successfully touched down on Bennu's surface to collect samples that will return to Earth in September 2023. These samples provide unprecedented insights into Bennu's composition and history, potentially shedding light on the early solar system. NASA's Sentry system continuously monitors and analyzes the trajectories of near-Earth objects, including Bennu. OSIRIS-REx data have helped improve our understanding of Bennu's orbit. Although the probability of a collision remains low, the proximity and size of the asteroid requires constant monitoring. The possibility of a gravitational keyhole, a small region in space where a planet's gravity can significantly alter an asteroid's path, makes it difficult to predict Bennu's future trajectory. Several strategies have been proposed to mitigate the risk of an asteroid impact. One of the most discussed methods is kinetic impact technology, which involves sending a spacecraft to collide with an asteroid, changing its trajectory. Another method is to use a gravity tractor, where a spacecraft hovers near an asteroid and uses its gravity to slowly change the asteroid's course. Nuclear diversion methods have also been considered, although they carry significant risks and challenges. The success of any mitigation strategy depends on early detection and accurate implementation. Astrophysicist Neil deGrasse Tyson spoke about the importance of studying asteroids like Bennu. Tyson has emphasized in several interviews and public appearances that while the probability of a catastrophic impact is low, the consequences would be severe enough to require preventive measures. He emphasizes the importance of missions like OSIRIS-REx not only in advancing our understanding of these celestial bodies, but also in developing possible deflection techniques. Tyson advocates international cooperation on planetary defense strategies and emphasizes that an asteroid impact is a global threat that transcends national borders. Countering the threat of asteroid collisions requires international cooperation. Agencies like NASA, ESA, and other spacefaring nations must work together to share information, develop technologies, and coordinate responses. The United Nations Space Agency, UNUSA, has produced guidelines for protecting the planet that emphasize the need for global cooperation. The potential economic and social consequences of an asteroid impact require comprehensive policies and contingency plans. Public awareness and education are critical to protecting the planet. Programs and campaigns that communicate the risks and the measures to be taken can help build support for funding and international cooperation. Cooperation with educational institutions and the media ensures that the right information reaches a wide audience, reducing misinformation and panic. Future Near-Earth Object, NEO, missions will build on the success of OSIRIS-REx, increasing our understanding of these celestial objects and improving our ability to mitigate potential threats. One of the main goals of future research is to improve our detection and tracking capabilities. Advances in telescope technology, both on the ground and in space, are critical to achieving this goal.
Next-generation telescopes, such as the Large Synoptic Survey Telescope, LSST, will provide an unprecedented view of the sky, allowing more asteroids to be discovered and observed more precisely. These telescopes are equipped with advanced imaging systems and data processing algorithms that can detect and track even small NEOs that were previously undetectable. In addition to improved detection, future missions will focus on asteroid characterization. Understanding the physical and chemical properties of these objects is essential for developing effective deflection strategies. Missions such as the European Space Agency's ESA Hera mission, which is expected to launch in the coming years, will conduct detailed studies of binary asteroid systems. Hera is completing NASA's Double Asteroid Redirection Test (DART) mission, which aims to test kinetic transport technology by deliberately crashing into a smaller body in the Didymos asteroid system. These missions provide critical information about the performance of kinetic impactors and the internal structure of asteroids, which is essential for planning future deflection operations. Important advances have also been made in the research and development of deflection techniques. The kinetic impactor method, in which a spacecraft collides with an asteroid to change its trajectory, has shown promise but still needs refinement. Future missions will focus on improving the accuracy of impact predictions and developing more efficient propulsion systems to deliver probes to target asteroids. In more detail, the concept of using a gravity tractor, a spacecraft hovering near an asteroid to gradually change its orbit using gravitational pull, is being explored. That method requires long-term position-keeping capability and precision navigation systems, both of which benefit from advances in spacecraft propulsion and autonomous control technologies. Another promising area of research is the use of nuclear devices to deflect asteroids. Although this method carries significant risks and is controversial, it remains a possible last resort against serious or imminent threats. Future research will focus on minimizing the risks associated with nuclear drift, such as fragmentation of the target asteroid and the possibility of radioactive contamination. Scientists are also investigating non-nuclear detonation methods, such as using conventional explosives to create thrust that could alter the asteroid's trajectory. International cooperation is the cornerstone of future research and technological development. The establishment of the International Asteroid Warning Network, IWN, and the Space Mission Planning Advisory Group, SMPAG, by the United Nations underscores the importance of a coordinated global response to asteroid threats. These organizations facilitate the sharing of information, resources, and knowledge between space agencies and scientific institutions worldwide. Collaborative missions, such as the joint NASA-ESA Asteroid Impact and Deflection Assessment (IDA) mission, exemplify the benefits of international partnerships in responding to the INEO challenge. In addition to technical progress, the development of strong planetary defense policies and countermeasures is critical. Governments and space agencies must work together to establish clear protocols for assessing and responding to potential impact threats.